We are jumping right into what I think is one of the most exciting papers to come out recently in generative AI. It's called RELIC, Interactive Video World Model with Long Horizon Memory.
Yeah, this one from Yikong Hong and the team at Adobe is a really big step, a major step towards, practical real-time spatial simulation.
Absolutely. The whole mission here, it seems, is to crack this trifecta of interactive world modeling. You need three things that, well, they usually fight each other. Real-time performance, long horizon streaming, and consistent spatial memory.
And RELIC, this massive 14 billion parameter framework, somehow manages to nail all three at the same time. It runs at 16 frames per second, which is basically the magic number for feeling interactive.
And the real genius, the core architectural insight, is all about how they handle memory. They're not trying to build some, costly, explicit 3D map of the world.
No, not at all. Instead, it uses these highly compressed historical latent tokens, and they're stored super efficiently right inside the transformer's KV cache.
Which is key. And by encoding those tokens with absolute camera poses, they get this implicit, but still 3D consistent content retrieval.
Exactly. Across huge time spans with almost no computational baggage. I mean, that's the secret sauce for the efficiency and the consistency.
Okay, so let's unpack this a bit. It's this grand vision and the specific conflict that RELIC is trying to solve.
Yeah.
The goal, and we talk about this a lot in world modeling, is spatial intelligence.
The ability to just step inside a picture and freely explore the 3D world behind it.
Yeah, for robotics, for autonomous driving, whatever. High-fidelity simulation.
It's the dream of a true digital twin, right?
Sure.
But the tools we normally use for this, autoregressive video diffusion models, they just hit a wall immediately.
A huge wall. And it's this fundamental conflict between performance and memory. If you want it to be real-time, you need, one-step or few-step denoising. You can't be waiting around.
For sure. But then if you want long horizon streaming, say stable rollouts for 20, 30 seconds, you need stability. Otherwise, you get this catastrophic drift where the world just breaks apart.
And then there's the third piece of the puzzle, consistent spatial memory. If I turn a corner, walk down a hall, and come back 30 seconds later, that chair I saw before,
It needs to be there.
it has to be there, and it has to look exactly the same. And for that, the model needs to store a long, long history of what it's seen in its KV cache.
And that's where the whole thing just peaks. Storing those long histories, it makes the computation just balloon, and you get this immediate memory bandwidth bottleneck.
So the moment your memory needs grow, your real-time performance just dies.
It completely collapses. So the challenge for RELIC is keeping a 14 billion parameter model fast while giving it what is essentially an infinite memory span inside this world.
So their solution wasn't to invent a whole new kind of diffusion model. It was this holistic engineering and architectural effort.
Right. They build on existing techniques, specifically the self-forcing paradigm, but they completely redesigned how memory and context are managed.
It's about making the architecture and the hardware work together, making them context-aware and just incredibly efficient.
Exactly.
So let's dig into that architectural genius, the compressed, camera-aware spatial memory. For anyone less familiar with transformers, the KV cache is, basically the model's long-term memory at Scratchpad.
And that's where they figured they could shrink things.
How did they do it?
Well, they realized you don't need full fidelity for everything the camera has ever seen. The long-term memory is made up of these highly compressed historical latents. They got about a 4 times reduction in the token count.
4 times? That's huge. Like from 120,000 tokens down to 30,000 or so.
Yeah, a massive reduction. And that's immense when you're trying to run this thing in real time.
So how did they get that ratio?
It was a pretty clever spatial downsampling strategy. The compression kind of interleaves different factors. So you have 1x, no compression, for the really recent high detail stuff.
Okay, that makes sense.
Then 2x compression for slightly older context, and 4x for everything in the distant past.
So it's like keeping a high-res memory of the last 5 seconds, medium res for the last minute, and then low-res snapshots of everything else.
You got it. It prioritizes the data based on how old it is. And what makes this actually useful for 3D consistency is how it's encoded. The latents aren't just stamped with a time index.
They're encoded with absolute camera poses.
Exactly.
Why is that absolute pose so critical, though? I mean, why not just rely on the previous frame?
Because without it, retrieving consistent content across big viewpoint changes is basically impossible. If I move, say, 50 feet and spin around, the model needs a global reference map.
A sense of where it is in the world.
Right. A sense of where I am to implicitly pull the right compressed scene info from that memory cache. The absolute pose is the coordinate system. It lets them sidestep the nightmare of running like an explicit 3D reconstruction system.
Okay, so that handles the memory pressure beautifully. Now, what about the teacher model? If you want the student, RELIC, to have this great long-term memory, it has to be taught by a consistent long-horizon teacher.
And that was a huge limitation in prior work. Standard video diffusion teachers, they're usually trained on really short clips, maybe 5 seconds.
And if your teacher only sees 5 seconds at a time, how can it teach a student to be consistent over a minute? It just can't.
It's like trying to teach someone how to run a marathon when your coach only knows how to run a 100-meter dash.
Exactly.
So the RELIC team, they focused on extending the teacher's horizon. They fine-tuned a powerful bidirectional teacher model based on WAN 2.1 to generate 20-second sequences.
20 seconds, that's 317 frames.
A huge jump. And they used a careful curriculum learning strategy. Started with 5-second clips for stability, then moved to 10, and then the full 20. It just ensures the supervision from the teacher is robust across these wide spans.
Which brings us right to the data. Because all this amazing architecture is useless if the training data is, garbage.
For sure. To learn 20 seconds of consistent exploration, you can't just scrape YouTube.
So why did real-world data fail for this task?
Well, real-world video has like 3 fatal flaws for this. First, the action distribution is totally imbalanced. It's all just forward movement. The model never learns complex lateral moves or tilting.
And the second flaw?
The actions are all coupled together. When you see someone turning, they're almost always also moving forward. So the model can't disentangle rotation from translation.
Which makes precise user control impossible.
Yep. And third, and this is a big one, is the lack of revisitation. In a normal video, you rarely go back to the exact same spot after a long detour. So the learning signal for long context memory is just super weak.
So they had to build their own perfect digital world first. That's the data set from Unreal Engine.
Correct. 350 licensed scenes, 1,600 minutes of 720p video, all carefully collected to ensure a balanced action space and, crucially, frequent viewpoint revisitations.
They basically forced the model to exercise its long-term spatial memory.
Had to.
And that control space is pretty granular, 13 degrees of freedom.
Very granular. 6 translational motions, dolly in, out, truck left, right, you get it, and 6 rotational motions, tilt, pan, roll, plus static. And they're all continuous relative velocity, so you get this really smooth control.
And the model uses those dual conditioning signals. We mentioned it, but it's worth repeating. Relative actions and absolute camera poses.
Right. The relative actions are for the instant gratification, telling the model how to move from frame to frame based on your joystick.
And the absolute poses are the integrated history. They're the proxy for retrieving spatial content across time.
You need both. You need to be responsive to the user and consistent in the world at the same time.
And they had that clever data augmentation hack, the time reverse augmentation. This feels like it was designed just to hammer that memory lesson home.
It's pure data engineering genius. They take a long sequence, they find a pivot point, and then they basically glue the forward segment to its time reverse version. It creates a palindrome.
A spatial palindrome.
Exactly. The model generates forward, then it generates backward, returning to the start. It explicitly forces the model to realize, hey, I should generate the exact same scene here that I did 20 seconds ago because the camera pose is identical.
It's just a really efficient way to strengthen that long context modeling. Okay, now for the training. This is, I think, the most technically impressive part of the paper.
I would agree.
We're taking that slow, high-quality 20-second teacher and distilling it into a fast, causal, few-steps student RELIC.
Right, using the self-forcing paradigm. And distillation is necessary because that teacher is just way too slow for real time. So to speed up convergence, they came up with this hybrid forcing for initialization.
Explain hybrid forcing. It sounds like they're feeding the model 2 different things at once.
They are. In the autoregressive sequence, they split the sample. The first video block uses clean, compressed latents for teacher forcing. It's basically a memory warm-up.
So they're giving the model the answer from the teacher for that historical context.
Giving it a head start, yeah. It guarantees stable memory retrieval before it has to generate from scratch. Then, the later blocks use noisy, uncompressed latents for diffusion forcing.
And that handles the recent context, where all the fine details matter.
Precisely. Combining them just gets you much faster convergence.
But the real technical breakthrough here for training these massive sequences is replayed backpropagation. I mean, with a 20-second sequence, that computation graph grows linearly. Back-propagating the loss must use just astronomical amounts of GPU memory.
Oh, it would be impossible. You couldn't fit it on standard GPU clusters. The graph for a 20-second rollout is just too massive to keep in memory.
So how do they get the benefit of that full 20-second gradient signal without storing the graph?
This is the elegant part. First, they generate the full 20-second sequence with autograd turned off. They stop the gradient, they use that rollout to calculate the score difference maps, and they just cache those scores.
Okay, so they know how wrong the model was over the whole sequence, but they don't have the graph to fix it yet.
Correct. Then step 2, they replay the rollout. But this time they do it block by block, and for each single block, they turn autograd on and backpropagate the cache scores that are related to just that block.
Wait, so by breaking the backpropagation into these tiny segments, they're reducing the peak GPU memory from the size of the entire 20-second rollout down to the size of a single video latent block.
That is the marvel of it. It's a time for memory trade-off that just unlocks training on the sequences that were previously impossible.
It's a great example of how clever engineering can be the real modeling advance.
And the engineering didn't stop there. To hit that 16 FPS goal, they had to squeeze every last drop of performance out of the hardware.
Oh, yeah. I mean, beyond standard stuff like torch.compile and flash attention, they made a critical call on the KV cache. They stored it in FP8 E4M3 format.
Quantizing the memory representation itself. Why FP8?
Because it essentially halves the memory usage, and it drastically cuts down the memory transfer time. Since the long horizon memory is the main bottleneck for latency, cutting the size and transfer time of the KV cache is non-negotiable for real time.
It's just a beautifully optimized machine. So let's talk about the payoff. What did all this complex work actually achieve in the metrics? Quantitatively, the results are crystal clear, especially on control. REIC gets the lowest relative pose error, or RPE, compared to competitors like Matrix Game or Hanyun Gamecraft.
And for our technical audience, relative pose error is the most critical metric. It measures how accurately the model translates your joystick inputs into camera movement. Lower RPE means better, drift-free control.
Exactly. It's proof that the dual conditioning and that balanced dataset really paid off. They also showed the highest overall visual quality and aesthetic scores.
But the real star of the show, the thing that proves the memory system actually works, is the qualitative stuff. Tell us about that rooftop bench example.
It's the perfect demo. The model generates a scene, the camera pans away, it explores a totally different part of the world for a long time, and then
When it comes back.
when the camera returns to the original spot, the model perfectly recovers the bench and the surroundings. It doesn't forget details. It doesn't generate artifacts. It's retrieving content that was out of view for a really long time.
That's the verification. It shows the compressed pose-aware tokens in the KV cache are really functioning as a persistent 3D memory, even though it's only generating 2D frames.
And it generalizes so well. They showed it exploring worlds depicted in oil paintings, comic book illustrations, vector art. The internal 3D awareness stays consistent no matter the style.
They also had a really important comparison to explicit 3D reconstruction systems, like Gaussian splatting.
Right. And while those systems are great at geometry, they often have visual artifacts, those weird floating points people call Gaussian floaters. RELIC, since it's a diffusion model in latent space, just avoids all of that. It gives you clean, stable outputs. It really makes a case that implicit spatial consistency can outperform explicit reconstruction for this kind of task.
Okay, so we have this massive model that solved the memory latency conflict through compression, long context teaching, and crazy training breakthroughs. But, I mean, no paper is perfect. What are the limitations here?
The main one is diversity and scene dynamics. It was trained on these curated, mostly static Unreal Engine scenes, so it doesn't really handle dynamic objects, characters, or scene changes well yet.
And while 20-second consistency is a huge leap, it still struggles with, extremely long videos. We're talking minutes, which you'd need for long-form simulations.
For sure. And the real-time performance is still dependent on very high-end hardware. This is not something you're running on your laptop anytime soon.
Still, RELIC feels like a massive milestone. It proves that you can combine these compressed historical latents with full horizon supervision to finally beat the consistency and drift problems that plagued all the earlier models.
It really does. It sets the new baseline for the next generation of simulators. That core architectural challenge of interactive consistency has, I think, been solved.
So if this efficient, memory-rich architecture can sustain 3D consistency over long horizons in real time, it just raises this fascinating question for the field,
Yeah.
What happens when we pair this foundational system with the next generation of dynamic character models or physics engines?
Yeah, what does that look like?
The path to genuinely immersive interactive world simulators ready for everyone to use, well, it just got a whole lot shorter.